They sort of rewrite the rules entirely, make us rethink everything.
Absolutely. They fundamentally shift our perspective.
And the Schrödinger equation, definitely one of those. I mean, it's a cornerstone of quantum mechanics, right? It totally reshaped physics in the 20th century, and honestly, it's still pretty mind-bending.
Oh, completely. It's probably one of those powerful tools we have for peering into that subatomic realm.
For sure. And that's what we're doing this deep dive. We've got this pile of your source materials, articles, notes, all focusing on this equation, and specifically where that famous symbol, the wave function, psi, actually comes from and what it means.
Right. Our mission today really is to unpack all that with you. We want to trace the thinking, the intellectual journey behind it, look at the mathematical steps Schrödinger took, which were quite surprising in places.
And really get into what this kind of strange wave function tells us, maybe what it doesn't tell us too, about how the universe works at the tiniest scales.
Yeah. Hopefully uncovering what its cell is all about. You should brace for maybe a few aha moments.
Or maybe uh-oh moments. We're talking about rethinking basics here, like location, certainty, even why energy seems to only come in these specific little packets at the quantum level. Let's get into it.
Okay, so where do you even start with something this big? The sources really point back to an idea that was already buzzing around physics, wave-particle duality.
Right, the idea that light acts like both a wave and a particle.
Exactly. You've got photons, these discrete packets, but then light also shows interference, diffraction, classic wave stuff.
Which is already a bit strange to get your head around.
It is. And then jump to 1924. Louis de Broglie comes along with this, well, truly revolutionary idea. What if all matter, electrons, protons, everything we think of as solid particles, what if they also have wave property?
Hang on. So, this microphone isn't just a thing. It has a wavelength. That feels deeply weird.
It feels weird, yeah. And for something like a microphone, that wavelength is absolutely minuscule, way too small to ever notice or measure.
Okay.
But for tiny things like electrons, it becomes significant. And de Broglie didn't just suggest it, he gave us a way to calculate it. He links momentum, p, to wavelength lambda, using Planck's constant h. So ppe.
Okay, so if particles are fundamentally waves, then the obvious next question is, well, how do these matter waves actually work? How do they move, evolve over time? You can't just use Newton's laws anymore, right?
Exactly. You need a new equation, a wave equation specifically for matter. And that's the challenge Erwin Schrödinger decided to tackle.
So how does he even begin? Does he just invent something totally new out of the blue, some kind of quantum magic?
Well, what's really fascinating, and the sources highlight this, is that he didn't start in some completely alien quantum space. He actually started with something very familiar, classical physics.
Oh, like what?
The basic equation for conservation of energy for a particle. Total energy, E equals kinetic energy, P squared over 2 meters, plus potential energy, V. E equals P2 meters plus V.
That's pretty standard stuff. How do you possibly leap from that to quantum mechanics? It seems like a huge jump.
Well, this is where the genius move comes in. Our sources really emphasize this point. Schrödinger realized he couldn't just use the classical numbers for energy and momentum. He had to replace those quantities with quantum mechanical operators.
Operators. Okay, that sounds like doing something to something else, like an instruction.
That's a great way to put it. An operator is basically a mathematical instruction. It tells you, perform this specific operation on whatever function follows it.
Right. So instead of saying energy is this value, it's more like apply the energy operation to. What does it act on?
That's exactly where the wave function enters the picture. But hold that thought for 1 second. Let's look at the operators themselves first. For energy, drawing inspiration from other quantum ideas like E, the operator E, involves how things change over time. It's E I just.
Okay, wait. There's an I in there, the imaginary number. Why is that showing up in physics? Seems weirdly abstract.
It seems abstract, but our sources stress that this I is absolutely crucial. It's not just some mathematical quirk. Putting I in the operator is what leads to solutions that naturally oscillate, that behave like waves. Without it, you wouldn't get wave-like solutions out.
Okay, interesting. So energy is tied to change over time. What about momentum? That's about movement through space, right?
Exactly. And the momentum operator, p hat, is linked to how things change over space. It involves spatial derivatives. So ijack, or just in one dimension, like along the x-axis, p0 is on ijack.
Okay, so Schrödinger takes the classical E equals P Twitter meter plus V. He swaps E and P for these time and space derivative operators, and then he has them act on This is where the wave function comes in.
That's precisely it. These operators, these instructions, they need something to instruct. They need a function to operate on. And that function is the wave function. It becomes the sort of central object. You plug the operators into the energy equation, apply them to A, and boom, the equation appears.
Right. Okay, let's see it then. The famous equation.
Okay, so the time-dependent Schrödinger equation, as presented in the sources, is I coordinate 2 meters plus VRT.
Wow. Okay. That is the one you always see. And that chunk in the square brackets on the right, the kinetic and potential energy parts.
That whole piece together is what we call the Hamiltonian operator,
Yeah.
usually written as A. It represents the total energy of the system in this quantum framework.
So you often see it written shorter, right? Like A.
Exactly. It compactly says, the way the wave function evolves in time is determined by the total energy operator acting on it.
Okay, so how AA changes depends on the system's energy setup. Now, you said A isn't just pulled from thin air. It's what the operators act on. But what is it physically? What does this A actually represent?
Well, think about the equation itself. The Schrödinger equation is a differential equation. And mathematically, its structure is that of a wave equation.
Okay.
And what are the natural solutions to wave equations in math and physics? They're functions, right? Functions that describe the amplitude or height of a wave moving through space and time.
So ART, the wave function, it just sort of emerges as the mathematical thing that satisfies this wave equation for matter. It's like the shape or the amplitude of de Broglie's matter wave.
Precisely. It emerges directly from the mathematical structure needed to make the operator approach work. It's a function, typically complex valued, that depends on position r and time. And here's the really key idea from our sources. This wave function is believed to contain all the information that can possibly be known about the quantum system.
All knowable information.
Okay. Its existence is a direct, necessary consequence of describing things like energy and momentum using operators instead of simple numbers.
It's complex valued. You can't go out and measure like 3 + 2i meters with a ruler. It still feels very abstract. What does it connect to in the real measurable world?
Right, and that's a crucial point. This required another massive conceptual leap, one that came after Schrödinger wrote down the equation. It came from Max Born.
Okay, so Born provided the interpretation. What did he figure out?
Well, the really surprising thing, the twist, is that AK itself, the wave function's value at a point, isn't directly observable. It doesn't mean the particle is right there.
Okay, so if Eke isn't the thing you measure, what is? What connects to an experiment?
Born proposed that what is physically significant, what you can relate to measurements, is the square of the absolute magnitude of the wave function, written as a K.
The absolute magnitude squared. Okay, what does that represent?
That quantity represents the probability density.
Yeah.
It tells you the likelihood per unit volume of finding the particle at position r at time t if you were to make a measurement.
Probability density. So not the probability at an exact point, but like how densely packed the probability is in a region.
Exactly. To get an actual probability, like the chance of finding the particle inside this little box, you have to integrate Eck over the volume of that box.
Ah, okay. So where Eck is large, you're more likely to find the particle if you look there. Where it's small, you're less likely.
Precisely. And this is a fundamental shift, isn't it? It's not saying the particle is somewhere specific and we just don't know it. The theory itself describes the particle in terms of probabilities spread across space.
That's a core concept. The wave function gives you potentials, probabilities, not certainties.
That's a major takeaway from the sources. And for this whole probability idea to make sense, the wave function has to be what we call normalized.
Normalized, meaning?
It means if you integrate S over all possible space everywhere, the total probability must add up to 1 or 100%.
Because the particle has to be somewhere, right? If you look absolutely everywhere, you're guaranteed to find it.
Exactly. That normalization condition is a crucial physical constraint built right into the math. It really underscores this probabilistic nature at the heart of quantum mechanics.
Okay, so the equation gives us S, and E gives us probabilities. Now, you mentioned quantization earlier, this idea that energy in atoms comes in discrete steps, not continuous values. Does the Schrödinger equation explain that too?
It does. Beautifully, in fact. It emerges naturally when you solve the equation under certain common physical situations. Specifically for systems where the potential energy, V, isn't changing with time. Think of an electron in a stable atom feeling the steady pull of the nucleus.
Okay, time-independent potential.
In that case, the equation simplifies. We get the time-independent Schrödinger equation.
Oh.
Notice the little psi now, usually used for these stationary states.
Right, that looks a bit tidier.
Yeah.
And this mathematical form, AS, is what mathematicians call an eigenvalue equation.
Eigenvalue. Okay, sounds important.
It is. Here, the chorus functions that are solutions are the eigenfunctions. They represent the possible spatial shapes of the wave function. For these stable states, you might know them as orbitals in chemistry.
Ah, orbitals. Okay.
And the corresponding values of E that make the equation true for a given tar are the eigenvalues. These are the specific allowed values of total energy the system can possibly have when it's in that state. So wait, solving the equation doesn't just give you the possible wave shapes, the orbitals. It simultaneously tells you the only energy values the system is allowed to possess for those shapes.
Exactly that. And here's the kicker for quantization. For systems where the particle is bound, trapped by a potential, like our electron in an atom, physically sensible solutions of heat only exist for certain specific discrete values of E.
But why? Why only specific energies? Why can't the electron just have any old energy value, like a marble rolling classically?
Well, our sources explain this comes directly from applying physical constraints, or what we call boundary conditions, when you solve the equation.
Boundary conditions, like what?
Things like requiring the wave function to be smooth and continuous, or, crucially for bound states, requiring that the wave function must eventually go to zero far away from the atom, but the electron has to stay bound. It can't just wander off to infinity with any energy. Or it must behave properly near the nucleus.
So it's the combination of the wave equation itself plus these perfectly reasonable physical requirements, like the wave can't be infinitely large everywhere, that mathematically forces the energy E to only take on specific discrete values.
That's precisely it. The quantization of energy, which is a huge puzzle in early quantum theory, just falls right out of the mathematics when you demand physically realistic solutions to Schrödinger's equation under boundary conditions. It's not something you add on. It's a direct consequence.
Wow. Okay, let's try and recap this journey. It's quite something. We started with the de Broglie saying matter acts like waves.
Which meant we needed a wave equation. Schrödinger built one, starting from classical energy, but crucially using operators instead of numbers.
Right, and these operators needed something to act on, which essentially necessitated the existence of the wave function as the container for all the system's information.
And because Schrödinger's equation is a wave equation, its solutions are these wave functions, mathematically speaking.
But the physical meaning wasn't immediately S itself. It took Max Born to say, no, it's S, the square of its magnitude. That gives you probability density, introducing probability right at the core.
A fundamentally probabilistic description. And then solving the equation for bound systems like atoms using realistic physical constraints.
Automatically leads to quantization. Discrete energy levels just pop out of the math.
Exactly. So the wave function's existence is required by the operator formalism, and its properties, combined with physical reality, reveal this probabilistic, quantized world.
It really did change the whole game, didn't it? All flowing from that initial wave hypothesis and the equation built for it.
It's quite an intellectual achievement when you trace it through like that.
So looking back at all the source material, the big takeaway seems to be Schrödinger's equation gives us the wave function. It doesn't pinpoint where a particle is, but instead maps out the probability of finding it. And almost as a bonus, it explains why energy comes in these neat little packets.
Yeah, this dive really shows how an abstract mathematical framework built on a radical new physical idea could unlock the fundamental operating system of the universe at that level just by following the logic and interpreting the results.
And maybe here's a final thought to chew on, something that comes up implicitly in these discussions. We normally think of probability as, a measure of what we don't know. It reflects our ignorance. If I flip a coin, the probability is 50-50 because I lack perfect information about the forces, the spin, etc.
Right. It's about incomplete knowledge in the classical world.
But in the quantum world, as described by the wave function framework from our sources, probability isn't about our lack of knowledge. It seems to be the most complete description possible. What does it truly mean about reality itself if its fundamental description is inherently probabilistic, not deterministic? That's something profound to ponder.